right, looks like my audio's on. Let's take a look at the participant list. Okay, I'm going to maximize that. And then I'm going to share my desktop. See if I put it here. Full screen mode. Then I've got my notes there. And I will log in from my other device. It looks like recording is on. Continue. Okay. Disconnect the audio there. All right. Can you guys hear me? Anyone?
Yeah, we can hear you.
Thank you. All right. Oh, and I almost forgot the most important thing, which is I will always start by talking about a favorite book, and I can't end that tradition now just because we can't be here in person. I'm not on campus today, so that's part of why Amazon Benedict Villars. So rather interesting series of, wait, what? It's not popping up. Physics was illustrative. Okay, a rather interesting series of physics books, nominally at the introductory level, but this is introductory level for biology students at MIT, is a series called Physics with Illustrative Examples from Medicine and Biology. It's 3 volumes, and frankly, I sometimes refer to it in research. I have had research students look at it to pick up particular topics. So if you want to see a different take on physics, maybe if you're interested in biophysics and you're thinking about pursuing that, or medical physics, and you want something a little more gentle to start off with, this is going to be more gentle than Philip Nelson's book or Molecular Biology of the Cell or whatever else. And Benedict is a biophysicist, and I actually took a class from a guy who did his PhD with Benedict. And Benedict started off as a pretty traditional physicist, and apparently his entry into biology was trying to figure out why the cornea is transparent while the rest of the body isn't, which if you think about it is kind of a strange problem. I mean, our skin, you can't see through our skin. Our internal organs, if you ever look at pictures of them, they're opaque. And yet somehow the cornea, despite being made out of cells just like everything else, is transparent. And with that, let's go to today's lecture notes. So last time we were talking about thin films, and the basic way we would solve any thin film problem is if we've got 3 layers, you figure out at each layer, is there a phase shift due to reflection? And there is if you're in a lower index medium reflecting off of a higher index medium. So in this glass air case, there would, be a phase shift of this reflection, but the light that enters the glass and then bounces off the second air layer, there would be no phase shift of that reflection. Then you also look at the phase shift due to the round trip distance traveled. And then you take the difference of those. And if the difference is an integer number of cycles, you've got constructive interference. And if it's a half of an integer, then you have destructive interference. And we went through several examples of that last time. What I want to do this time is talk about where each of these effects come from and how they change under different circumstances. I've been just asserting that there's this half cycle phase shift on reflection. And we made, I think, a pretty straightforward case for why there's a round trip phase shift. But how does that round trip phase shift change when the light's coming in at a different angle? So let's start with the half cycle phase shift. And to start with a half cycle phase shift, we're going to just look at a much simpler problem, a two-layer problem. So we're going to have a plane wave coming in a medium with index n1. And we could write that plane wave as some amplitude, e sub I, a unit vector showing the polarization, z hat, if this is going in the x direction, and then our usual exponential. And of course, there's a reflected wave. And that reflected wave, well, in the exponential, we're going to reverse the sign of k, because now it's going in the minus x direction instead of plus x. We're going to write the amplitude in this form. We're going to write the amplitude as some coefficient whose value we have yet to figure out, but I'm going to call it R12, meaning reflection in layer 1 off of layer 2, times the original amplitude, EI. So you could just think of that as if R12 was 0.1, that just means that the amplitude of this field would be 10% of the amplitude of that field. And then in the other layer, the other medium, excuse me, we're going to have a field that I'm going to write in this form. And the exponential is slightly different because now we're in a different medium, so k is changed. K is now n2k naught instead of n1k naught. And we're going to again write the amplitude in terms of the original amplitude times something I'm calling T12, meaning transmission from layer 1 to layer 2. And again, you can think of it as if T12 was 0.5, that would just mean that this amplitude was half of that amplitude. And when they go through, of course, light is always split like this. You actually see this every time you look at a window. If you notice, if you're inside and you look through a window during the day, you don't see a reflection off of the window. That doesn't mean that there isn't any light reflected off the window. It's just that the light that's reflected off the window is pretty faint and the light coming from outside is pretty bright. So you never notice it. But at night, when you look at a window, you see, assuming it's well lit inside and dark outside, you're not looking at a well lit patio or something, you see a reflection, and it's pretty strong. It's not that the window has magically become more reflective at night. It's just that at night, there's no light coming from the outside, or very little light. So the only light you're seeing coming through that window is the light that reflected off with this amplitude, R12. And so we're essentially right now trying to figure out how to calculate the amplitude of the light reflected off of the window. So we're going to start by noting that the electric field has to obey the wave equation right here. And in the wave equation, we take the second derivative of E with respect to X. Now, in order to take a first derivative, your function has to be continuous. This is one of those things where if you think back to freshman calculus, at some point the professor harped on some things with continuity and limits, but then you spent the rest of the time just trying to remember which formula you use for which type of derivative. And you probably thought, like any good physicist, all that nitpicky proof stuff, I don't need to worry about that. And certainly that was reinforced for me as a freshman when my professor would delight in making fun of the one math major in the room, deliberately doing things that weren't mathematically rigorous. But now it turns out that we need that stuff in sophomore physics. We can't take the derivative unless the field is continuous, and we can't take a second derivative unless the first derivative is continuous, all right? And that's actually kind of a tall order because in this medium, the field takes on a very different form than it does in this medium. We're taking two very different formulas, two very different mathematical expressions. and we're insisting that they have to be continuous here. So what that means is that if I take x equals 0, and I calculate the field on this side, and then I plug in x equals 0 to calculate the field on that side, I better get the same number. I don't have to get the same number way out here and way over there, but I have to get the same number right here at the interface at x equals 0. And likewise, if I calculate the derivative of e on this side and then plug in x equals 0, I better get the same number that I would get if I took the derivative of this expression and plugged in x equals 0. Now, that seems like a tall order because we've got 3 fields and 2 conditions. But notice that the field on the left, it's not like there's 2 completely separate fields here. I've written the field in 2 pieces to elucidate 2 physical processes. But in fact, at any point in space, you just measure an electric field. You don't measure 2 electric fields, you measure 1 electric field. It's the sum of this and this. And because it's the sum of 2 waves that are oscillating and traveling in different directions, the actual behavior could be pretty complicated, but at the end of the day, whatever number I get, if I go into the lab and I measure the electric field at this point in space where my cursor is, I get a number. Well, I get 3 numbers, it's a vector, but you know what I mean. I get a specific quantity. I don't get 2 separate things. I don't get an incident and a reflected. I just get the sum of these 2. So all of that means that the electric field on the left side is this. It's the sum of this exponential going to the right plus this exponential going to the left. And the one going to the left has a different amplitude. The field on the right is much simpler. It's just this. And then likewise, I can take the derivatives. And remember that whenever I take the derivative of an exponential, I get back the original exponential multiplied by whatever was multiplying my variable in the exponent. So both of these exponents have I n1 k naught, I n1 k naught. So that pulls out there. But here it's minus I n1 k naught. So there's a little minus sign here. On the right, it's much simpler. And again, these are 2 very different expressions for the derivative. They don't have to match at every point in space. That would be impossible. They only need to match at the interface. They only need to match when we plug in x equals 0. Any questions so far? Going once, going twice. This is perfectly clear. You're ready for me to do some algebra with these? Okay. So we plug in. When we plug in x equals 0, the e to the I k naught x goes away. It just becomes 1. But we've still got this factor of e to the minus I omega t. Now, luckily, that's the same on both sides of the expression. Likewise, both sides have an ei and a z hat, but those are the same on both sides. So the only thing I'm left with is 1 plus r12 equals t12. And then, likewise, when I do the same thing for the derivative, I've got a whole bunch of stuff that goes away on both sides. Both sides have an ei, a z hat, an e to the minus I omega t, and I k naught, same here. So I'm left with this equals this. And now I've got 2 equations and 2 unknowns. I've got 1 plus r12 is t12, and n1 times 1 minus r12 equals n2 t12. So do a little algebra, and I get t12 out of the first equation, out of the second equation, excuse me. I get the t12 equals this complicated expression with n1, n2, and r12. But it's also equal to this much simpler expression. So I can set these 2 things equal to each other and just solve. And when the dust settles, I get that r12 equals n1 minus n2 over n1 plus n2. So now I have a way of calculating the amplitude of that incident wave, if it will let me. I have a way of calculating the amplitude of this reflected wave in terms of the amplitude of this incident wave. Any questions? Let me ask you this. What if N1 is 1, air, and N2 is 1.5, glass? What's going to happen? What can you tell me about the value of R12? Anyone? Bueller? Bueller? Nobody? Nobody wants to guess? Ah, okay, somebody typed negative into the group chat. Yes, the reflection coefficient becomes negative. So what that means is that if we go to the next slide, it means that the amplitude of the reflected field, let me get rid of some of this stuff here. All right, I just erased a bunch of stuff. It means that the amplitude of the reflected field is equal to the amplitude of the incident field multiplied by a negative number. So if the incident field was a vector pointing up, then the reflected field is a vector pointing down. And when a wave goes from pointing up to pointing down, it has gone through half a cycle, because from here to here is half a cycle, and then back to the next peak is a full cycle. So that's where the 1/2 cycle phase shift comes from. If N1 is less than N2, then we're multiplying the reflected wave amplitude is equal to the incident wave amplitude multiplied by a negative number. That's the half cycle phase shift. But if we multiply by a positive number, well, a peak is still a peak. It might be a smaller peak because we might be multiplying by 0.1 instead of minus 0.1, but it's still a peak. So we don't get a phase shift. All right, so that explains why I keep saying that when the wave comes in, we get a 1/2 cycle phase shift here, and we get a 1/2 cycle phase shift there, and those two cancel out because this one came in at its peak, hypothetically, or if it came in positive, it comes out negative. And this one comes in at, I don't know, whatever point in its cycle. Maybe it's just halfway up now because it's gone through a fraction of a cycle. And it gets reflected down. And so these two phase shifts cancel. The only way that this thing, you're thinking, well, this is pointing down and that's pointing down. The only way that these two things are going to cancel is if by the time it gets to here, it's now pointing up because it's gone through some portion of its cycle. Any questions at all on that? Anyone? This is all as clear as BK7 glass from Schott Manufacturing. This is as clear as the finest glass that my friends in the Optical Society would be happy to sell you. There are no questions. Okay, well, if there are no questions, here's a question. We've established that fine, it has to, we're gonna get that half cycle phase shift. We haven't said yet a word about why it is that people use magnesium fluoride. I kept using magnesium fluoride as the example last time, and I said that in World War I, it was a big deal to develop magnesium fluoride anti-reflection coatings for lenses on bomb aiming equipment. But let's talk about why magnesium fluoride as opposed to something else. So let's break this process down into a whole bunch of steps. All right, we got an incident field. Some of it gets transmitted with amplitude T12. Some of it gets reflected with amplitude R12. Of that transmitted field, some of it gets transmitted again. So now that amplitude will be the product of two transmission coefficients, because the fraction that got through here was T12, then a fraction of a fraction gets through there. And it also got a phase shift because it traveled through this distance, so it went through whatever fraction of its cycle. And I'm writing e to the I phi instead of e to the I n2k naught d because I don't want to carry so many symbols around. All right, so it gets to here. Now, of the stuff that got to here, a fraction of it got in, a fraction of it gets reflected, then a fraction of that fraction gets transmitted. So we've got R12 here, and there is a typo here. This should be, actually, I think I can fix that in, I think I can fix that in Acrobat. Let's do that right now. Back to view page. This wait. Okay. Get rid of the group chat. Let's just fix that right now. No, I don't want to highlight. I want to annotate my PDF. I want to edit my PDF. And now I managed to, oh. It's converting it to editable. It's 90% done. Okay, so I'm going to change this to, that was R23, that was R23. It's just this that I forgot to change. So I'm going to add some text right here. I'm going to put the text right there, 2-3, if I can. All right, thank you for bearing with me during that edit. All right, and now we're ready to continue. Except I want to be in view mode, not edit mode. So how do I switch? Okay, I close that toolbar. You know, we don't have these sorts of tech problems with the chalkboard, I'm just saying. Okay. So we've got these two amplitudes, all right, R12 and R23. And we're adding these up. Now, of course, there are other passes. There's some fraction of a fraction that gets reflected here, and then a fraction of that gets reflected again. And we could keep adding up more and more of those reflections. And each reflection is going to be a fraction of the amplitude of the previous one. And it's actually a fun problem in an infinite series to solve. We're not going to do it right now, but if you want a puzzle to work on, that's actually a fun one. Try working on it and then show me your solution, because it leads into a lot of techniques used in more advanced realms of physics. But the key thing is that I keep hammering on how each successive step is just a fraction of the previous step. So we get a fraction of a fraction of a fraction. We're getting exponential decay. So this first reflection and second reflection, those are the two largest reflections. All of the others are going to be weaker. So we could write the reflected field as R12 plus the second reflection, which has these two transmission coefficients and also this reflection coefficient. And then I'm going to assert that these two transmission coefficients are very close to 1. And here's the beauty of that assertion. If I didn't make that assertion, I could instead do all of the remaining steps. And it turns out that even though this product of reflection coefficients is not 1, it's probably 0.9 or so, all of these other reflections add up to 0.1. That's not at all obvious, but however much this product of transmission coefficients falls just short of 1, all of the other reflections compensate for it. And again, for now, I'm just going to assert it. If you want to test it, you can do so. So in the end, we get that the reflected field is 0 if R12 plus R23 times this exponential phase factor is 0. And let's see here, if this is a quarter cycle thick, then it goes through a half cycle on the round trip. So if it goes through a half cycle on the round trip, someone want to tell me what this exponential factor should be? Anyone care to hazard a guess? Think about the round trip. Think about how many cycles it goes through. What does a wave get multiplied by when it goes through that number of cycles or that fraction of a cycle? No guesses? Let's see here. A full cycle, it goes through a half cycle. Now, a full cycle in radians would be 2 pi. So a half cycle in radians would be pi. So 2 phi would be pi. Now you may be thinking, wait, shouldn't 2 phi be 2 pi? But remember that phi is the phase shift that it goes through on one pass from left to right. When it goes from left to right, it gets a phase shift e to the I phi. And it's a quarter wave thick. So that's going to be, let's see, a quarter of a full cycle. That's 2 pi over 4. That's pi over 2. So this is e to the I pi over 2. And then when I raise that to the power e, when I replace that with the power e to the 2i phi, that's going to be e to the I pi. Now I want you to think way back to the first day of class when we did complex numbers. What's e to the I pi? Anyone? Anyone? Really? E to the I pi. I'm not going to make this easy for you. Let me find my annotation tools and we're going to draw something. Complex plane. Unit circle. We will just pretend that this is a, let's make one more attempt at a circle. One more attempt at a circle. Well, wait, I've got other drawing tools there. Ooh, I didn't even know I had that. Oh, okay. Having fun with my drawing tools now. All right, back to that. So we'll go to here and we'll drag it. Oh, I see how this works. Okay. All right. So unit circle. Here we've got 0. Here we've got pi over 2. Here we've got pi. So in the complex plane, if this is 1, please don't overthink it. What's this? Cosine pi plus I sine pi, someone wrote in the group chat. Very good. But what's sine of pi? And what's cosine pi? All righty, it is -1. I'm gonna go to dental school because that was like pulling teeth. Okay, so I've got to move my annotation toolbar out of the way. All right, so we've got that we've got R12 minus R23. And that difference is 0 if this expression is true. If N1 minus N2 over their sums equals N2 minus N3 over their sums. If I divide the top and bottom of the left by N2, and I divide the top and bottom of the right by N3, then I get this. And this looks like the same expression on both sides, just that I replaced the ratio n1 over n2 with the ratio n2 over n3. So these expressions would be the same if this is true. All right. And let me get rid of that annotation that was messing everything up. All right. So all of that is true if n2 squared is n1 minus 3, or n2 is the square root of n1, n3. So that just means that n2 is going to be intermediate between n1 and n3. And if n1 is 1, air, and n3 is 1.5, glass, then n2 should be about 1.22. But it is really hard to find a material that, 1, has refractive index n 1.22, 2, will attach to glass. Getting two materials to bond with each other is not always easy. That's why the glue and adhesives industry makes money, because it's hard. And 3, will be mechanically stable, meaning that if we put this layer on there and we get it to stick, it won't be brittle, it won't fall apart, it won't go to pieces when it's on an airplane that's vibrating, or when it's on a microscope lens that comes into contact with a specimen. Some specimens actually touch the lens. So that makes it very difficult. So to this day, magnesium fluoride is a popular material. And there are people who make very good livings doing nothing but trying to make coatings for glass. Their focus is less on optics than on the material science, but it's actually a very good career that a lot of physics graduates go into. Thin film people can make a career out of that. All right, so more numbers. If we calculate the value of R12, we're going to get, I did this wrong the first time, so then I replaced it with an absolute value. We're going to get minus 0.2, or its absolute value is just 0.2. Well, intensity is proportional to the square of amplitude. So if the amplitude gets multiplied by 0.2, the intensity gets multiplied by the square of 0.2, or 0.04. So most glass has a reflectance of roughly 4%. Now, of course, not all glass has an index of 1.5, but 4% is a pretty good rule of thumb when you're setting things up in the lab. And then if we put this coating on, remember, we're going to be taking R12 minus R23. So now R12 changes, because now we have to compute that for the reflectance of magnesium fluoride, and then we have to compute the reflectance of glass when it doesn't have air next to it, but instead has magnesium fluoride next to it. And so we take these two numbers, we subtract them, we get that. That's the amplitude reflection coefficient of this coating. Then we square that, and we get 0.014, which is about a third of regular glass. So what I want you to take away at this point is that the reflection phase shift comes from the fact that the field at the boundary has to match the field on the other side. It comes from solving this matching problem, and you get that the coefficient depends on the difference of the refractive indices. So if you're going from low to high, you get a negative amplitude reflection coefficient. If you're going from high to low, you get a positive reflection coefficient. And that's going to determine how strong the field is when it's reflected. You've got reflections from the two layers. And it's the difference between those two reflectances that will determine just how strong your ultimate reflection is. I've thrown a lot at you, so I want to pause again for questions. All of this is as clear as a sheet of glass with a anti-reflection coating that has 1.22 as its refractive index. Really? Nobody has a question? Yeah, Kenneth.
So I have a question for like, I noticed that all the examples of a light ray is basically going straight to towards the material.
Mhm.
What if like it's going at an angle? Would the equation for like for a reflection would still work?
If it's going at an angle, then what we have to do is go to the next slide that I was going to talk about.
Oh, okay.
Yeah, that's exactly my next topic, so thank you. Any
Uh,
other questions on the previous topic, though? All right, hearing none. So Kenneth is right to ask about those, not just because I was planning to talk about, but because if you look at examples of this in real life, since we're not live, I can't pass examples around the room like I normally would. But if you think about when you've looked at oil slicks, the colors change with angle. The same is true if you have glasses with anti-reflection coatings. It's something that the optometrist makes some good money off of, so they try to push it. In my opinion, the anti-reflection coatings are overrated. The glare I've never found to be much of a problem. Maybe if I was playing sports or if I was in some sort of security job where I was doing high stakes things in the field, I'd have a different view, but I think the glasses for sports are a completely different thing altogether. But in any case, if you look at those anti-reflection coatings, you will see that although they're perfectly transparent at normal incidence, or not perfectly, but very close to perfectly transparent at normal incidence, they do have a little bit of color at other angles. And conceptually, it comes from the fact that, well, this distance here has changed, right? This round trip distance is different. Now, it is very tempting, but wrong, to think that the entire path inside the coating is extra, and so therefore we just need the hypotenuse of the right triangle, all right? If that was all it is, then this would be a pretty simple problem to solve. But that's wrong for two reasons. For one, if you look at this diagram up here, you see how there's this extra distance traveled on the left side? Because, yes, some of the light goes in and it goes through the hypotenuses of those two right triangles, and it comes out here. But there's this distance here, so we're certainly going to have to deal with that. Also, it's the x component of the wave vector that determines how much the phase changes as we move along the x-axis. So if I'm somewhere on the upper left, that should have been upper left, not upper right. I'll change that rather than doing more edits in the middle of the talk. If I'm somewhere on the upper left, okay, well, a wave could have come to me this way, or a wave could have come to me that way. Now, either way, if the waves are going, the waves have to go through both a vertical displacement and a horizontal displacement. But for the vertical displacement, that is going to be ky times, the phase shift due to that is going to be e to the I ky times y. Okay? And remember that ky is n sine theta. Let me see if I can find my annotation tool again. Okay, that is a very bad attempt to draw a cursive K. I could use my tablet, but I really don't want to switch devices. N sine theta, K naught. All right, it's N sine theta, K naught. Now, what do we know about N sine theta in these different layers? What did we learn a couple weeks ago about N sine theta? There's a law about that. There's a law about N sine theta. First discovered by Ibn Sahl in the Middle East, but in our textbooks named after a Dutch guy who did it several hundred years later. Come on, somebody must remember that.
Snell's law. Snell's law.
Snell's law. Yeah, what does Snell's law say?
N1 sine theta equals, or N1 sine theta 1 equals N2 sine theta 2.
Yep. So n sine theta is the same in here and in here. So all of the upward motion, whether it goes upward via this path or upward via that path, all of the upward motion contributes the same phase shift. It's the horizontal motion that's going to contribute different phase shifts. So the path that goes through the film is going to have an extra phase shift 2d times kx, or 2d k naught cosine theta 2. All right. And so let me get rid of all of that annotation again. Okay. So we could just replace 2d over lambda over n2 with 2d cosine theta 2 over lambda over n2, because we're just replacing the value of kx we had before, where all of the motion was entirely along the horizontal axis. So kx was just nk naught. We replace it now with nk naught cosine theta. And everything else still applies. The rules for the reflection coefficients still apply. We still have to say that, okay, we got air, we've got oil, we've got glass. There's a half cycle phase shift here. Is there a reflection phase shift here? No, because we're reflecting off of a lower index medium. The only difference is that the round trip phase shift is 2n2d cosine theta 2 over lambda instead of just 2n2d over lambda. All right, so we get in the end that lambda is 2n2d cosine theta 2 over m plus a half if we want constructive interference. But now here's the thing that everybody messes up. People try to use, cosine theta is 45 degrees. Now, cosine theta in the air is 45 degrees, but cosine theta in the oil is going to be something else because, again, that law named after Snell but first discovered by Ibn Saul. So we have to do that math. We have to figure out cosine theta 2 using the fact that the index of air multiplied by the sine of the angle of incidence is equal to the index of the oil multiplied by the sine of the angle in the oil. We solve for the angle theta 2 in the oil, and then we take its cosine. There are always people who want to skip that step. And you can't skip that step. If you skip that step, you're going to mess it up. And then you're just going to be living for partial credit, and that's no way to live. But if we do all of that, we can plug in and we can get numbers. Any questions on that procedure? Today's recitation activity walks you through that procedure. Whether or not you're registered for the recitation, you can go and download the activity. It's basically a step-by-step breakdown of a problem very similar to that. There's one other thing I want to point out from the recitation activity, which is that I've included a Mathematica file with it. And I need to get rid of some of these things. I don't know if you can see them on your screen, but there's a bunch of Zoom controls that block things on my screen. I have posted a Mathematica file on the site for the lecture class under course documents, Mathematica files. It's also posted with the activities. If you look in that Mathematica file, first I define a whole bunch of functions that I use in the calculations because I do the exact calculations. So far, I've only shown you guys how to calculate what angle or wavelength or layer thickness will give constructive or destructive interference. Just figure out, well, when does constructive or destructive interference happen? But I haven't shown you how to calculate what the reflectance would be, especially in cases where the interference is neither purely constructive nor purely destructive. If you want to learn that, take one of our upper division optics classes. But in here, there are a bunch of functions to find, and all you have to do is hit Shift-Enter. That just tells Mathematica, hey, don't just display them on your screen, actually commit them to memory. And then if we go in here, we have got a plotting command. So first we tell it what we want the indices to be. I set up some slightly different numbers. We tell it what the thickness layer will be. And the two things that we don't tell it are the wavelength and the angle of incidence. And the reason why we don't tell it that is because I want to vary those. We're going to vary the wavelength along the x-axis. So we're going to set this up so that you see a plot of reflectance versus wavelength. And right now, the angle of incidence is 0, but we can play with that angle of incidence via this slider bar. We can make it whatever we want it to be. And what we should notice is that as we play with this angle, if we go from small angles to large angles, do you see how the reflectance minima, the wavelengths that give us minimum reflectance or destructive interference, you see how those wavelengths get shorter? Based on what we saw in here, can anyone hazard a guess as to why? It's staring right at you. If you look at the formula for the wavelength, there's something staring right at you that depends on the angle. The formula for wavelength, we got lambda equals all of this multiplied by cosine theta 2. Now, if the angle of incidence is 0, cosine theta 1 will be 0, theta 2 will be 0, cosine of 0 is 1. If the angle of incidence is non-zero, then the angle inside the second layer, or the second medium, will be non-zero, and the cosine will be less than 1. So everything gets shifted to shorter wavelengths. Now, I'm not going to go through all the details of this, but some people are really uncomfortable with the phase argument. If you're really uncomfortable with the phase argument, if you really want to figure out, okay, what's this distance and what's that distance, and let's take the difference of the two. And here I walk you through how to do it. It's 2 pages of derivation. It's just first doing some geometry, all right? We'll figure out what the tangent of this angle is and relate the tangent of this angle to the layer thickness and this distance up here, because you have to figure out where does the ray go out. Figure out this phase shift here in terms of y, this distance, and sine of theta 1. And then we also relate the path length to theta 2 and the layer thickness. Then we figure out the number of extra cycles of oscillation while covering this distance, the number of extra cycles of oscillation covering that distance, remembering that there are different wavelengths in the two media because they have different indices of refraction. We get something complicated. We can simplify it slightly using Snell's law because we get a few signs of different angles, and Snell's law will help us simplify that. Then we take the difference, we use some trig identities, and finally we get this expression here, which was exactly what I said we could get from the argument using the component of the k vector in the phase. And one reason to show this is that this kind of geometric approach actually gets used a lot in material science. If you're doing X-ray or neutron diffraction to analyze molecules and materials, and even sometimes in photonic crystal research with visible light. So it does get used, but I think that the more fundamental idea is the phase argument. So if you want to work through that geometry, it's all laid out here. Any questions? Well, in this class, we don't go through a lot of it, but it's worth noting that there's a whole lot more to thin films than just a single layer. In an intro class, we just walk you through the single layer argument, because if you really understand the single layer argument, then in more advanced classes, you can build up to the multi-layer films. But multi-layer films do some pretty amazing things. So here's a slideshow from a company called Semrock, which makes multi-layer films. And they do a lot of things with those multi-layer films. Let's go to the beginning of it. They make multi-layer films with many, many layers in them. And why they make them is because look at these curves of transmittance, which is 1 minus reflectance versus wavelength. Everywhere where you see low transmittance, that's high reflectance. Everywhere you see high transmission, that's low reflectance. So what they've got is they've got something selective. They've got something that has very, very high reflectance for certain ranges of wavelengths and very high transmittance for other wavelengths. So this is selective. This is a way of selecting which colors will get through and which ones won't. And here they go through different designs. And one problem is that getting low transmission over a range is easy. Getting high reflectance over a range is also easy. What's not easy is getting high and constant reflectance. Here you see the reflectance is high throughout this range. The problem is that it's not constant. Different colors will be reflected by different, transmitted by different amounts. This is the goal. Making a filter like this takes a lot more work. Don't worry about any of the details of how they did this. But people put a lot of work into designing filters like this. And you might think, well, once they've got a design, why not stop there? The short answer is that if the design takes a whole lot of layers, that's expensive to manufacture. So people continue to work on ways to make multi-layer films that will achieve the same result with fewer layers because it'll be a much faster thing to manufacture. Some people will make filters like this, where it only transmits a very narrow range of wavelengths. Some people will make filters like this, which perfectly transmit below a certain wavelength and nearly perfectly transmit and nearly perfectly reflect above that wavelength. And all of that just comes from optimizing the choice of layer thickness and layer material. And it's not just based on optical considerations. It's not just based on saying, oh, well, I want a filter that is transmitting at these wavelengths and reflecting at this one. It's also a matter of saying, okay, if I do that, what refractive index would make that happen? Do I have a material that I can purchase at reasonable price and that I can get to bond to glass in my manufacturing process? So that's what a lot of people work on. That's actually a field that hires a lot of physics graduates, often people who got bachelor's degrees in physics and either learned on the job or went and got a master's in engineering or material science. All right, I'm not going to say anything more about multi-layer filters. I'll just say that if you want to work through more practice of these single layer things, there is a recitation activity. For those of you who are enrolled in the recitation, please remember to keep turning in recitations. You get full credit as long as you do it. It's just for practice, but you only get credit if you do it. That is a 1-unit class. It does show up on the transcript and it hasn't been canceled. You still have to do the work. Also, I will probably not be in my office nearly as much going forward. So calling me on my office phone is iffy. but I compulsively check my email, and so you can always reach me that way, and then we can set up a Zoom meeting. Any questions on anything? All right, then. If there are no questions, we will resume on Monday. Have a good weekend.
You done now?